we're going to get some general rules about how to construct these moment diagrams with, yeah, anyway, we're going to get some general rules about how to do this stuff. So we have a point loads, we have distributed loads down here. We have a pin joint at A, a roller joint at D. So we won't have any axial loads whatsoever, no tensile forces. We just have shear and moments. And we're going to consider a little section out of the middle. This little section out of the middle. What's going on? And we can find the summation in the y direction. Well, that's positive v minus minus v plus delta v right here. Positive v, take away v plus delta v, v plus delta v. And then we have to also add the force in the middle, which is, the force in the middle is the distribution of forces, W as a function of x, times delta x. So there's the forces in the middle. And they all have to sum to 0. Which when we work this out, we get delta V equals W delta X. So we can get a derivative now. Derivative of the shear force equals W of X. So here the arrows are pointing up. If they were pointing down, you'd have a negative sign. Some people will, in fact, a lot of our drawings, you'll notice the arrows are pointing down. So just be aware of the pluses and minuses. Be careful about that stuff. So here we have the sum of the moments has to also sum to 0. Sum of the moments about 0.0 is what we're talking about. So we get an m plus delta m in the positive, negative m here, and we have this force W delta X, and it's acting somewhere in the middle. We don't know exactly where, so we're going to use the variable K just to say that the distance, the lever arm is K times delta X. It's not delta X over 2. It's maybe K is a half. Maybe K is closer to 1. Maybe K is closer to 0. We really don't know. And we're not going to worry about it for right now. We'll figure it out later. So the moments, well, we have the one shear. This shear is not going to count because we're taking it about 0.0. So this shear will count. Negative V delta X. There it is, right there. Negative M, also in the clockwise direction. Positive M plus delta M, counterclockwise direction. Now that K factor. The moments due to this force. And we have the force, Wx delta x, times the lever arm, K delta x. And it's negative because it's going in the clockwise direction. And we solve for delta m. We get this expression right here. Now, the reason K goes away is if you divide by delta x and take the limit, you're going to get the derivative. And, well, as delta x goes to 0, this term is going to go to 0 right here. So we're left only with V. dm dx equals the shear force. dv dx equals W, the force distribution. Which we observed that earlier, that the maximum of M is going to be where the shear force equals 0. We saw that on the earlier example. That was an interesting note. The slope of the shear diagram, this is going to be the distributed load intensity. That's W. The slope of the moment diagram is equal to the shear. Maximum or minimum moment occurs when the shear equals 0. Remember, when the derivative equals 0, it can either be a maximum or a minimum. You don't know until you check that out. Integral forms. So now we can get the shear force B to C. We integrate this, and the change in moment from B to C, we integrate this. We integrate the shear force. Okay. So these two equations right here spent, all this math surrounding it, all this math over here, zeroes in on these two equations. What you need to know. Watch out for signs, though, also. If the arrows of W point down. Okay. Now, we need to consider, what if there's a moment applied at a single point, or a force applied at a single point, where we have these two force diagrams, that the change in V is going to equal F. Well, that's pretty easy to see. Total force has to equal 0. It's V plus F minus V minus delta V, which means delta V is going to have to equal F. That's it. Pointing up. If the direction is reversed, then you'd have a negative sign. Delta M, well, this one's real easy. Delta M in this case is, well, it's just like what we found before. D, and we'd have to do the DMD other stuff. So now we have a step in M. When crossing the application of a moment, and that would be this side of the diagram here, we have the moment before and M plus delta M minus M naught. So the change in moment is M naught. And this is point application. This is, although the diagram shows a delta X is infinitesimally small. Just remember that. This is application ideally at a point, which is why we're not considering the moments of this. It's not distributed forces anymore. It's a point load. Force at a point or moment at a point. How do we use it? So we have a beam like this, and we say, first of all, we notice this force here, and so there's no forces or moments out here. The beam ends. It's the end of the beam. And the delta F is, and it's pointing down in this case, so it will go negative. In this case, the arrow is pointing down. In this case, the arrow is pointing up. In the next case, the arrow is pointing down. So we would use this equation here. The change in shear is negative F. So, boom, we got that. Negative 2. And for 2 meters, it won't change. dV dx equals W. 0W, no change. From between here and here, it changes. So the slope, W is a negative constant, negative 1.5 kilonewton meters. The slope of this would be negative 1.5 kilonewton meters. We're going from negative 2 to negative 5 over 2 meters. So the slope is negative 1.5. So there's your shear moment diagram. dm dx, remember, that's equal to the shear. So it's, oops, there we go. The slope of the moment is going to be just the shear force right here, which is negative 2 over 2 meters. That will get us down to negative 4 kilonewton meters. We have a linear equation here. dm dx equals whatever this linear equation is. It would be negative, I'd have to go figure it out. You solve for the equation of this line. So m is going to turn into something quadratic, since the shear is going to have a slope times x. When you integrate that, that means the moment is going to be going as x squared. So it'll be some sort of quadratic. Okay, so this is what we just talked about. Now the moment diagram. This is the tricky one. So going from 0 to 2, the moment diagram then, it just goes linearly from 0 to negative 4 kilonewton meters. And this goes through the math of that. Delta M, negative 2 kilonewtons to over 2 meters. Because this is the shear force, negative 2 kilonewtons. Here's another example. The overhang. Let's see. I wanted to finish up. I wanted to get the second part of the moment on this example before we move on. So let's go back. The shear here would be the slope of this. It changes by 3. So we ought to be able to get the slope-intercept form of V. V equals 1 kilonewton, and the slope is going to be 1.5. Double check that. At 2, we get negative 2. When x equals 2, we get this point. When x equals 4, that's 1 minus 6 or negative 5. So this is the equation for the shear force. So dm dx equals, it's going to start at negative 4, by the way. That's a constant of integration. Equals 1 minus 1.5 x. Integrating this, m equals x minus 0.75 x squared. And so when we plug in x equals negative 2, we ought to get a negative 4. So that's negative 2. X squared is 4, would make it 4. So negative 2 minus 0.75 times 4. And that would be 3. Negative 2 minus 3, negative 5. Something's wrong. Oh. Do I need a constant somewhere? I think I do because I forgot my constant of integration. So to match up, m has to equal -4 when x equals 2. 2 minus 3 is -5. 2 minus 3 is -1. So we have to have a -3. That was kind of a weird line there. So let's check at 4. It should be equal to -11. So 16 times 3/4 is -12. And 4 minus 12 is -8. Minus 3 is -11. Okay, so I just forgot the constant of integration earlier. So there's our equation for the moment. And so that's how you draw the diagram. It's not too tough. Ending the video here, going on to the next example.